All right, guys, are you ready for this? We are going to go over our chapter 3 and 4 waves study guide. So we're going to start over here with mechanical waves. The type of mechanical waves: sound waves, water wave, and seismic waves, which are earthquakes. And then our EM waves are radio, microwave, infrared, visible light. It's the only EM wave that we can see: ultraviolet, the UV, X-ray, and gamma. So the types of media that they move from: solid, liquid, gas. The plural for that is media. So you might see a question that has media on it, and it really is just the plural of medium. Okay, so don't let that fool you. So the types of mediums that an EM wave go through would be solid, liquid, gas as well, but we're going to add that empty space vacuum. So parts of the wave, we have two different types of waves for a mechanical wave. We have transverse wave and a longitudinal wave. So the parts of a transverse wave are a crest and trough, and for a longitudinal wave, we have a compression and rarefaction. Remember that a longitudinal wave might also be called a compression wave. So the parts of the EM wave is a crest and trough, because all EM waves are transverse waves. So it really is just this here, which is going to be our sound wave, right? Our sound wave that has different parts, a compression and rarefaction. Otherwise, all the other types of waves that we looked at have a crest and trough, okay? So mechanical waves move fastest in solids and slowest in gas. And remember, that makes sense because in a solid, the particles are packed super tight together. And so if we are moving through from particle to particle to particle, it's going to move fastest where our particles are closest together. And with a gas, our particles are farther apart. So that also makes sense why they're going to move slowest in a gas. Okay, so let's come on over to the EM waves. They are going to move fastest through our empty space. Well, that's because they are generated by the sun, right? And so we have the sun here, that with the nuclear reaction, the hydrogen and helium fusion, giving off all of that light. So EM waves do not require matter to move. Mechanical waves do require matter to move. So with an EM wave, there is no matter out in empty space, so they're going to move fastest there and slowest in a solid where there's lots of matter, okay, tightly packed. So make sure you are very familiar with everything that's on this chart. So what is being transferred during the movement of a wave? Energy, not matter. That's why you bob up and down in that wave pool, or why the ducks or someone swimming doesn't get thrown to the front part of a lake when a boat goes by producing a wave. Okay, because it's going to transfer the energy, not matter. All right, so what's happening in this picture here? The light waves change direction. Remember, that's one of the properties due to refraction. So this is when we put the pencil in the water and we look at it underneath and it looks like it's split. Why is this happening? Refraction occurs when a light wave changes speed. The beam of light changes direction because light waves slow down as they move from air into water. Light travels faster in air than in water, so that water is more dense. And so here is coming I'll make this a little bit darker here so you can see. So here it's coming here, but then, okay, as we are entering, because remember when we talked back on how our light waves want to travel in a straight line. So this would want to continue moving forward like that. However, it has that appearance of it being broken. Of course, that pencil is not broken, but it just has that appearance of that broken, changing directions a little bit when it moves into a different medium. Okay, so All right, so let's take a look at this. We've got ourselves a transverse wave with crests and troughs, right? And so you need to be able to identify the parts of a transverse wave. So these are all of the electromagnetic waves are going to follow these same words, okay? So the crest is the top part of a transverse wave, because here's our wave, right? Up and down and up and down, okay? All right. So the top part of the wave is the crest, the bottom part is the trough. So we have wavelengths. Wavelengths are from one part of the wave to the exact next part of this, same part of the next wave. So we're going crest to crest, as in this case here, or trough to trough, as in this case here. All right, so amplitude is going to be the measurement from the rest position to the crest, or the rest position to the trough. And the amplitude is how much energy that wave has. So every time you see amplitude, you need to think energy, all right? Okay, so this question asks here, I know this didn't show up super well, so let's just go ahead and trace that out. All right, so if you know this distance here, if the distance between the crest and the trough is 4 meters, well, what's the wave's amplitude? Explain. So the wave's amplitude would be 2 meters, because if we look at this picture here, we know that the amplitude is from the rest position. I'm going to go ahead and make this purple so we can see it different. Rest position to crest. That's what our amplitude is. So if you know the whole distance from trough to crest, then you just divide it by 2, and that is going to give you your amplitude, because the distance from the rest to the crest and the rest to the trough is going to be the same. So it rises above the rest position and falls below the rest position with the same amount. So however high this is how high that is. So if you know the entire thing is 2, then you just divide by 2. So the amplitude is measured from the rest position to the crest, or the rest to the trough. So if you know the entire distance from crest to trough, divide by 2. All right, so then we have to label the longitudinal wave. Now, this sometimes is known as a compression wave because of the compressions and rarefactions. All right, so the areas where they're closest together is our compressions, where they're farther apart is our rarefactions. And wavelength would be compression to compression, or rarefaction to rarefaction. Okay, so make sure you're able to label that on a longitudinal wave as well as a transverse wave. Okay, guys? All right. So short answers here. Describe the relationship between amplitude and energy. All right, so remember, you're putting these two together. Increase amplitude is going to give you increased energy. Decrease amplitude is decrease energy. So since amplitude is the maximum distance a wave moves from its rest position, a large amplitude wave carries more energy than a small amplitude wave. So if we have our rest right here, and we have up and down and up and down, crest and trough there, and then we have a second wave here that we're comparing it to, okay? So we're going to be able to say that this wave here has a higher amplitude and has more energy because the amplitude is higher. So the distance from rest to crest is higher than this here. Okay, so be able to identify, if you're looking at 2 different waves, which one has more energy. So the higher the crest, that indicates how high it's rose above the rest position. That is because of the increased energy. Okay. All right. So describe the relationship between frequency and wavelength. So our wavelength, remember, is our crest to crest, or trough to trough, or compression to compression, or rarefaction to rarefaction. Okay. So this is what we did remember when I had my hands out and I was clapping, we stretched out at a really long wavelength. okay, or a really short wavelength. So we're going to start with the high frequency first. So it's going to be faster. So this is where you're going to put your hands really close together and see between your two fingers here, there's not a very long wavelength, but listen to the frequency. Okay, so really high frequency. So we have a very short wavelength and a very high frequency, very fast frequency. And then when we have a very long wavelength, like if you stretch your hands out fully from side to side, okay, here's our frequency. Okay, clapping my hands, bringing it forward just like what we practiced in class. So if I have a really long wavelength, I'm going to have a very slow frequency. So they're inversely proportionate. If one goes up, the other goes down. Okay. All right, so here is the law of reflection with the angle of incident and the reflected ray. So make sure that you are able to reproduce this, or be able to identify the parts of a wave like this. All right, so we know we have our incoming, so it's coming in, our light source coming in. That's our incident ray. Everything is on the same side. It's all going in, okay? So then it's going to hit this mirror, whether it be an actual mirror. And remember when we talked about diffuse and regular or specular reflection, this also could be like a water, like a really clear lake. Okay, so the angle coming in and the reflected angle. So the incident ray and the reflected ray, they're going to be the same. And we are going to be measuring from this normal. Remember, this is an imaginary line that forms a right angle perpendicular to the mirror surface. So the angle of incident is determined from the incident ray to the normal, and the angle of reflection from the reflected ray also to the normal. So if the angle of incident is 30 degrees, what is the angle of reflection? What law supports this? So if the angle of reflection is 30, then if the angle of incident is 30, then the angle of reflection is also going to be 30, because they have to be the same. So the law of reflection states that when a wave is reflected from a surface, the angle of reflection is equal to the angle of incident. So they have to be the same. Okay. If one decreases, the other decreases. If one goes up, the other goes up. If one is 32, the other is 32. Okay? All right, because they are the same. Okay? All righty. Only EM waves can move through empty space, vacuum. In a transverse wave, a measure of the distance from trough to the next is the wave's wavelength. Okay, in a longitudinal wave, the particles move parallel, like this, to the direction in which the wave travels. In a transverse wave, it goes perpendicular. So this was the going up and down of the hand when the wave traveled that direction. Okay, the distance from one crest to the next crest is a wave's wavelength. Okay, just like this question asks you from trough to trough, this is crest to crest. Okay, the sun's energy can move through space because it travels as an electromagnetic wave. So remember, we write that as EM. Okay, the frequency of the wave is the number of wavelengths that pass by each second. That's just a definition. Okay. A longitudinal wave makes particles in a medium move back and forth parallel to a wave movement. So we've asked the same question in a couple of different formats. So make sure that you are associating longitudinal and parallel, and transverse and perpendicular. Okay. All right, so here's a longitudinal wave. Describe the relationship between amplitude and compressions. So when we have increased amplitude, then the compressions are going to be closer together and the rarefactions are going to be farther apart. Increase amplitude, increase energy, decrease amplitude, decrease energy. Okay, so if you were comparing two compressional waves side by side, remember we looked at this in our reading essential, we are able to see that with a high amplitude wave, the compressions are closer together and then the rarefaction particles are farther apart. Okay, so describe the relationship between amplitude and crest in a transverse wave. Since amplitude is measured from the rest to crest or trough, but crest in this case because that's what the question is asking us. Waves with higher amplitude energy will have a higher crest. All right, so if there's more energy behind that wave, then it's going to move farther off of the rest and it's going to give us a higher crest. Okay, so here we're going to sort these words. Absorption, so that these are going to be the properties of matter. Tinted windows is going to absorb some of those light rays coming in. It's not going to be quite as bright on the inside for the driver, not quite as hot. So it's going to transfer some energy to the medium it travels through. So that window is going to absorb some of that radiant energy, that light energy. Transmissions, clear windows, goes right through. Remember, all materials are going to absorb some EM waves, but some materials absorb more and some materials absorb very little. So a transmission is going to absorb very little. So you're going to be able to see right through it, like when we looked out into the courtyard. Light passes through glass windows, passage of light through an object. Reflection, so we see yourself in a mirror, anything that's shiny, chrome on a car, the wave is going to bounce off that surface. Refraction, changing speed when moving into a new medium. So that was that pencil in the cup. And then diffraction is spreading out around the barrier. When the sound wave has the same wavelength as the opening. So remember we talked about in class about the doorway being the width of a wavelength. That's why it spreads out beautifully and goes right down the hallway. We can hear the kids on either end of the hall without seeing them, because these waves are going to come through, and then as they pass through that opening, then they're going to spread out. That's diffraction. Okay, so sound waves is a mechanical wave. So these are some of the terms that we've already talked about. That's a longitudinal, travels through matter, solid, liquid, gas, not a vacuum. It's produced by vibrations. All waves are produced by vibration. The wavelength, distance from compression to compression or trough to trough. Frequency, number of wavelengths that pass a certain point each second. In the unit for that would be a hertz. So how does temperature affect the speed a sound wave travels? Increased temperature, increased speed. This is due to the increased thermal energy and movement, the kinetic energy of those particles. So if a sound wave is moving from particle to particle, if we increase the temperature of those particles and they're moving faster, then that's going to have that wave move faster through that material as well. Okay, so increase speed, increase temperature, increase speed. How does the type of wave affect the speed a sound? How does a type of matter, affect the speed a sound wave travels? So sound waves travel quicker through materials that is more dense. Particles are closer. So they're going to be fastest in the solid and slowest in the gas, where our particles are farther apart. If they're going from particle to particle to particle, where it's packed closely together like a solid, that's going to make it go through there quicker. In a gas, they're a little bit further apart, right? Not even touching. And so it's going to go a little bit slower. So pitch. Pitch is the perception of how high or low a sound seems. Frequency determines pitch. Increase frequency, increase pitch. Decrease frequency, decrease pitch. This is when we did that tone regulator tone with the really high frequencies, and we try to figure out like where you could hear it and where I couldn't hear it and all of that. So that tone generator, that's what we were looking at. It's a perception of how high or low. Okay, so what is loudness and how is it determined? Loudness is a human sensation of how much energy a sound wave carries. So the words that we're going to put here is it going to be loud? It's going to have increase energy. Remember, we wrote this in our margin. And if it's going to be soft, we're going to have a decrease energy, just like a whisper. Okay. So what is the relationship? Okay, we go on to talk about this and write this down here. What is the relationship between amplitude and loudness? The higher the amplitude, the louder the sound. So if you're shouting, you're putting an awful lot of energy behind that. It's going to be very loud. But if you don't put very much energy, so if it's a low amplitude, then it's going to be quiet. It's going to be like a whisper. Okay. All right. So then this section on EM waves, they are organized by wavelength. The unit for that would be a nanometer. It's 1/1 billionth of a meter. So crazy small. So on the left side here, we have the types of waves, and they are written in order of wavelength. And if you look here, we have our radio waves, which are the longest, all the way down to our gamma rays, which are the shortest. So be familiar with the type of wave and the examples that we use in our real life, okay? So the microwaves, cell phones, actual microwave ovens, the visible light, remember that's the only one that we can see. That's your rainbow, that's your RGB, the ultraviolet, sunburn, which is why we wear sunscreen, okay? So remember, the shorter the wavelength, the faster the frequency. So super fast, right? Super fast, super fast, super fast. So remember, when we're trying to figure out wavelength and frequency, we're going to hold our hands right in front of us. We're going to look at that distance, and then we're trying to clap and see how fast it is. Okay, so the shorter the wavelength, the greater the frequency. Okay, so then we have this section on how light interact with matter. Something is transparent. It's going to allow almost all of the light to pass through. It's going to have a nice clear image. So that is a glass window. Okay, where you can see right through. It doesn't look fuzzy or blurry at all. When we held up the plastic wrap, we could see right through it. A clear glass, you can see right through it. So there's lots of things that's transparent. Translucent, a material that allows most of the light to pass through. So we can still see that light is coming through, except it's not like perfect. So it's going to be a little blurry. So that's going to be frosted windows, wax paper, tracing paper. So this might be like in some of the showers at your house where you can't see like directly in, and it's just kind of like a hammered look. That would be a translucent. Okay, opaque, you can't see, no light makes it through. So a material that does not allow any light to pass through. So construction paper, book, aluminum foil, go on and on and on. If you hold it up to light and you can't see anything through it, then that's opaque. Okay, if it's perfectly clear, it's transparent. If it allows some light, but it has a blurry image, then that would be translucent. Okay, all right. So light waves are measured in nanometers. So this last little section talks about color. Why do we see color? When light waves of different wavelengths. So when we come back up here, we see, and on the teaching video I had about this, I talked about how in this section here, with these wavelengths and these colors, that each of these wavelengths is associated with a particular color. So that the red is up near the 700, and the violet of RGB is at the 400. So each of those colors has their own unique wavelength range. Okay, so let's keep that in mind. So when light waves of different wavelengths interact with an object, the object absorbs some light waves and reflects others. Since white light is a combination of all the white light, you see color when the white light breaks into different wavelengths. So this is when we're looking at that prism, and we could make the rainbow. I'm sorry, but that's a rainbow. When we position the light in the prism just right, you can do that when you're watering the grass in the summertime. Not today, but watering grass in the summertime, you can see that rainbow with the light breaking up into different colors. So why do we see? So that's when we see it break up. But then what about why we see something that's red? Or why is it that we see something that is yellow? So example, so a red rose reflects the red wavelengths and absorbs all the other wavelengths. So we see something as blue, it absorbs all of the wavelengths but reflects blue. Why we see a yellow banana absorbs all but reflects yellow. Okay. So, let's see. Here we go. We're just about done, guys. Hang in there. Okay, so in which direction does light travel away from its source? Draw a picture to illustrate this. So we've got to have a light source first. That's something that emits its own light, or that we light like a candle, or we turn on like with electricity for a light bulb. Anything that emits its own light. We don't emit our own light. So the light source travels away from the source in all directions. So we could have this going out in all directions. In all directions. Okay, you see an object because the light reflects off of an object and then up into your eyes. That book that you're reading is not making its own light. You're reading that book, that physical book, because a light is on. If you turn that light off, you can't read that book anymore, because if it doesn't emit its own light, we require a light source to bounce off of that object and up into our eyes. Okay, so what is scattering? Draw a picture of it. So this is when light traveling in one direction are made to travel in many different directions. These are dust particles in the air you see when sunlight shines through a window. So light wants to travel in a straight line. It always wants to travel in a straight line until something gets in its way. And in this case, it's like dust particles that are in the air, and they will just bounce off, because here comes your light. It wants to travel in a straight line. But then we've got all of these little dust particles, and it bounces off of it. And then you can see those dust particles that are normally occurring here in our air. So that is scattering. Okay, regular reflection and diffuse reflection. So regular reflection is going to be on that smooth surface, like a smooth water surface. A smooth surface reflects light rays traveling in the same direction at the same image. And so have the nice sharp image. So with this, your water is smooth, okay, and the light coming in bounces off, and a nice crisp image will return to your eyes. So you'll see a nice crisp image. So this is smooth water. So remember when we did this on my teaching video, then I had that picture that I was showing you, comparing the two regular and diffuse reflection. Okay, but then we have this other. So this is going to be something with a little bumpier surface. So it's a rough surface. So these light waves still want to come in straight. Okay, they still want to come in, but the surface that they're bouncing off of is irregular. So it causes them to bounce up, not perfect. The law of reflection, with this one here, it's bouncing up at the same angle. But this one here, it's bouncing off all irregularly, because it's hitting those water waves the water itself is making it hit at different angles. So a rough surface reflects light rays traveling in the same direction. So that light ray is coming in, but it's going to bounce it back at different angles. So that is going to produce a blurry image. So then we have a few energy transformations here. So we're pretty good at energy transformations. So energy transformations that result in light. Okay, so we have a candle that's chemical. So the wick is specially treated, that when we set it on, when we ignite it, when we add flame to it, it will produce light, thermal energy. Also, it's hot. So fire does the same thing. So a flashlight, that battery is stored chemical energy that when you turn it on produces light. We have nuclear, that's that hydrogen and helium fusion, produces an enormous amount of light. And then a light bulb, or anything that's plugged in, like a lamp, is going to produce electric to light energy. Okay, and then that wraps that up. So make sure that you scroll through and stop this video wherever you need to make sure that you have all the correct answers for the upcoming test. Because you know what, guys, you're going to be able to use this study guide. Okay, so your copy of the study guide you're going to be able to use. So let's make sure you have all the right answers, okay? All right.